Assalamualaikum, hi everyone. So as promised, I'm going to show you again how to solve the thermal effect problem that we did in our last tutorial class. Okay, so here is the problem or the question. So basically we have a rod CD that's heated from 30 degrees Celsius to 180 degrees Celsius, and at the lower temperature there's a gap between C and the rigid bar, which is 0.7 mm, and we have to determine the force that is developed in rod AB and EF caused by this increase in temperature. Okay, so first what we need to do is we need to see whether this temperature increase will cause CD to elongate more or less than the existing gap, which is 0.7 mm. Okay, so how to do that? We use the thermal deformation formula, which is delta T equal to alpha delta T times M. Okay, so here delta T here is, in this case, is 180 minus 30 degrees Celsius equal to 150 degrees Celsius. Okay, so you have the value of alpha, and also into this formula you will get the deformation of CD caused by the temperature increase. Okay, so you will see that CD actually elongate more than the existing gap, which is more than 0.7 mm. So definitely it will. So once this happens, this problem become a statically indeterminate problem, and it will also cause internal forces to develop in all rods. Okay, in rod CD and also in rod EF. Okay, so for statically indeterminate problem, remember we have 5 steps of solving. Okay, and the first step is always start with finding the value of F, or the internal force. Okay, so equilibrium equation. Okay, so as usual we draw the FPD of the rigid bar. Okay, so we have FAB, we have also FCD, and also FEF. Okay, so write the equilibrium equation. Okay, assume that outward is positive. Negative FAB minus FEF plus FCD equal to 0. Okay, so by looking at the problem, or by the observation, we know that FAB is actually equal to FEF. Okay, okay, so we assume that assign this as FSD. Okay, SD is for steel, since both are, so we can write as FSD. So rewrite this equation here. It becomes negative 2 FSD plus FCD equal to 0. So this is our equilibrium equation, our first equation, and obviously we cannot solve for the internal forces using we need to form another equation, which is compatibility equation. First we need to consider the geometry of deformation of the whole structure. Okay, so this is our second step. So for this step, it is actually a little bit tricky. Okay, you have to think carefully or imagine what happened to the whole structure when it is loaded. Okay, in this case when CD is heated and push the rigid bar. Okay, my suggestion, it is always helping if you draw or sketch what is happening to that structure as a whole. Okay, based on the drawing, and you can then write the geometry of deformation equation. Okay, so let's draw the deformation of the whole structure. Okay, so this is the CD rod. Okay, and if there's no rigid bar, it will elongate, let's say this much, caused by the increase in temperature. Okay, so this is delta T. Okay, however, since there is a rigid bar, okay, so let's say this is the initial position of the rigid bar. Okay, this elongation here is actually constrained. Okay, constrained by the internal rod CD. Okay, when the rod touch or push the rigid bar. Okay, so again, the internal force actually constrain this deformation here and push down the rigid bar to a lower position. Okay, then this elongation caused by the this position here is actually the position at which the bar is pushed up by the elongation of the two rod at the side. Okay, rod AB and also EF. Okay, so again, this position here is by the elongation of these two rod AB and also EF. Okay, or the stainless steel rod, and we can say that this is the final position of the bar. Okay, and this is the initial position of the bar, and this is the deformation of rod CD caused by the internal force. Okay, and again, this is the delta or deformation of the or elongation of the rod. Okay, so and also don't forget you have the gap here, which is 0.7 mm. Okay, so if you want to write the deformation of the whole structure in terms of stainless steel rod, you can write delta ST is actually equal to, okay, the whole line here or the whole elongation here, which is delta T CD, okay, minus this deformation, okay, delta F CD, okay, and also minus the gap, which is 0.7. Okay, okay, again, this elongation here, okay, we can see the distance here is actually equal to the whole distance or elongation of this CD, okay, caused by minus the deformation of CD caused by the internal force, okay, and also minus the gap, the existing gap, which is 0.7 mm. So this is basically the geometry of deformation. Okay, so we're done for the step number 2. Now move on to the step number 3. The next step is you just need to write the force deformation relationship and also the force thermal deformation relationship. So delta is equal to F L over AE, and also delta T, or the deformation caused by the or thermal effects, is equal to alpha delta T L. Okay, so just substitute this into the geometry of deformation equation that we in the second step just now. Okay, then it will give us the compatibility equation. So now you have two equations, so you can solve for the internal force. Okay, so the internal force can be solved by solving both equation, the equilibrium equation and also the compatibility equation, simultaneously. Okay, then you can get the internal force, the value for internal force. So solve simultaneously. Then this will give you the value of F in all rod. Okay, in all three rod A, B. Okay, then you're done. That's all. Thank you.